I wanted to do this episode on this type 2 partial fractions, repeating linear factors, to specifically highlight one of the nuances on what is so different about this repeating linear factors versus non-repeating linear factors. And there is something very special that we do when we solve the repeating linear factors in terms of taking an extra term and defining an extra constant. And I'll talk about that. So I just wanted to take this episode just exclusively focusing on why we need to do that and give some perspective, taking some simple examples on how does it work and where does the extra term come from. And some of these things I must have already repeated and covered in the detailed episodes or solving the exam problems for type 2. But I think in some of the episodes I must have gone too fast, or I think I need to still do some justice to this concept. So I want to just dedicate few minutes just for this particular pattern, and you guys can watch this in as a companion guide to those videos, or you can watch this and see them later so that you can get a better understanding. Nevertheless, let's just jump into this particular nuances of what I'm referring to. So let's say I'm taking two examples of two rational expressions, okay, and both of them are the same type 2 repeating linear factors. Okay, if you see here, in this case, x plus 2 is repeated and all the factors are linear in nature. And in this case, if you see this, if you expand this as a square minus b square, if you apply the concept of a square minus b square, and you can open up this bracket, so you'll get these two expressions. And in that case, this one and this one gets repeated, okay? So that's what's happening. And all other terms are linear. So we know that they are type 2 repeating linear factors. Okay, we know that. And but what is the difference in the outcomes when we resolve? This is the rational expression and this is the partial fraction in both the cases, right? This is the rational expression and this is the partial fraction here. Okay, so let me just create some space here and so that it's very clear. Oops, sorry about that. Okay, all right. So now what is the difference in the partial fractions, right? The type 2 input is same on both the rational expressions. In the output, and we have solved this in different other episodes, so don't worry about how this answer came, but I'm just assume that this is the answer. So the partial fraction, when this rational expression is decomposed into a partial fraction in this format, and then when you substitute the a and b, this is how it gets. And in this case, when we decompose this rational expression into a partial fraction, this is the final output that we get like this, okay? And the fundamental difference in both the things is, in the first case, the partial fraction has got two constants, a and b, and two terms, like this is term 1 and this is term 2. And in the second case, the partial fraction has got three constants, which is a, b, and c, a, b, and c. And we got three terms, right? This term 1, this 1, this 2, and this is 3. So the interesting thing is, whenever you're trying to solve, and let's say in the exam you get the rational expression either this or this. So the $1 million question that you have is, how would we know? Because this is going to be a first step, right? If you see, let me just erase this. Okay. So when you do a partial fraction problem, when you solve, the first step is to put this. This is the first step. And this depends upon the type of the problem, type 1, type 2, or type 3. Over here also, if you see, this is your first step to just substitute the constants and then solve for it. That's the only important step in partial fractions. The rest of the maths is very simple. These two steps are the most important step. How do you do that, okay? And to get that right, the question is, how do you know in advance if you're given these two equations? Let me pull this up. If you're given these two equations, whether the corresponding partial fraction will have, whether you should start with two constants or you should start with three constants. How do we know that? That's the question that we need to ask, because that's where the confusion is, right? And typically there is a way to do that. Now let's understand why we do those things in a certain way, okay? If you see the peculiar way over here, if you see the peculiar way of that is this term, right? Where there is an extra term. Hold on, let me just erase this out. Okay, there is an extra term in the middle which has one of the factors of the repeated one. The repeated one is x plus 1 the whole square, okay, if you see here. So it has the linear format to the degree 1. It's not repeated with the power 2. That's the last term. So the last term is same in both in terms of the whole repeated factor is taken. But in this case, in the second example, there is this extra constant term which has a constant in the numerator, and in the denominator it has the linear factor of the same repeated version without the power. It's just a degree to 1, right? And in this case it's not there. That's the one that's missing. Okay, because if you see here, these two terms are split evenly. In this case also, if you split this x plus 1, you have one term, and sorry, for x minus 1 you have the first term here, and this term is same, but this term is extra, right? So why does this term come extra here, and is that the right way to do that? That's a question we're asking, like how do we do that? Okay, now to understand this, let's take some two different examples. We'll keep it simple and just understand how the calculation works, and that will make your job very easy on why we need to do this and when we need to do this, okay, and how we need to do that. So let's take a completely different rational expression, which is 1 over x squared plus 2x plus 1, okay? And if we factorize the denominator, which is what we need to do in all the partial fractions, whenever we have a rational expression, we need to see whether we can factorize that. And when you factorize that, if you see, this will become into this format where you have x plus 1 the whole square kind of format. And if you expand this is what you get. So this I can simplify as x plus 1 the whole square. And let's assume that I'm going to decompose this into a partial fraction, and I'm just substituting this constant to be a, and this is how I get the answer. So this is the rational expression, and this is how, let's say, assume that this is what the answer I'm getting, okay? So what do we observe here? The observation is the post factorization. From here we factorize to this. So post factorization, which is this, right? Post factorization, the denominator has got two linear factors. Okay, that means it makes us the type 2 problem with linear factors, okay? But what's happening is the linear factors in denominator are linear repeated, but the partial fraction, this partial fraction, right, it just has one term and just has one constant, right? And this is the right answer. So this particular partial fraction has just one term and one constant in this case. And the denominator is x plus 1 the whole square. And in example 2, let's say you have been given this rational expression. Let me just scroll the screen up. Okay, let's example 2, let's say I've given you this rational expression, and the answer for this, if you decompose this into partial fraction, this is going to be your answer. This is going to be a solution where you have got two terms, and the reason is very simple. If you check out here, if I start from here, right, if I start from here and simplify that, take the common denominator, multiply and do a cross multiplication, I get this rational expression. So I get that, okay? And that's the reason we know that the the partial fraction for this rational expression has to be this, and we have proved that, okay, just for simplicity. So we know that there's a solution, okay? And hence we can take this rational expression as it is, and we can split the denominator because it's repeated. I'm repeating it twice, and that's linear repeated. And the partial fraction for this, since we have proved from here, we get this 2. If you see this 2, we are taking it here. And then I can substitute the constants a and b here. This is a and this is b. And what do we observe? Again, post factorization, if I factorize the given expression, post factorization, the denominator has got two linear factors, okay? And that makes this the type 2 linear repeated problem, okay? But if you see the output, the partial fraction has got two terms, whereas in this case, the denominator is still the same, right? If you see the denominator here, it's x plus 1 the whole square. And in this case also, it's x plus 1 the whole square after you simplify, okay? But the partial fraction, in this case, the expression is too simple. So the partial fraction and the rational expression after factorization is the same. We cannot simplify it further. So it's the same term. But if you see the denominator, so let's say instead of this problem, I would have given you this problem, 1 upon x plus 1 the whole square, which is this. It would have been the same thing. The rational expression would be just simple one term, and you would have put this, okay? So the question is, the denominator is same, x plus 1 the whole square in both the cases, over here also, but the partial fraction comes out differently, okay? And the reason it comes out differently is because of the LCM. So let's see what do we observe here, okay? In both the examples, the denominator is same, which is x plus 1 the whole square, which is what is I highlighted in yellow, okay? But because the LCM works out the same in both the cases, okay? What does that mean? For example, if the partial fraction given to us is this, right? The LCM of both of this is still x plus 1 square. Although there are two terms, if you take the common LCM, it's still x plus 1 the whole square. And the first case, since there is only one term, the LCM is still going to be 1 plus x plus 1 the whole square. So that the post the LCM, right, the denominator is the same, and that's the reason we will not know whether the partial fraction will have 2 constants or 3 constants, because based on the expression we will not know, because the LCM works out the same in both the cases. And that's the trick here, and that's where the confusion is, and that's the reason we need to take that extra term. Hopefully this was clear, right? Both the examples have same denominator because the LCM works out to be the same in both the cases, but there are different number of constant and different number of terms in the numerator of the partial fraction, and this is what I was trying to explain. Okay, so how do we solve this, right? That's a question, the same question that we're asking. How do we know in advance how to solve this problem? Should I take 2 constants, or should I take 3 constants, or 1 constant? How do I solve about it? Okay, and the answer is very simple. What you do is you first factorize. Okay, just do the factorization in both the cases, and after factorizing it completely, okay, you see how many factors the denominator has. Okay, in this case, after factorizing, we have got 2 factors, 2 linear factors. We cannot simplify this any further. And in the example 1, again after factorizing this, again we have got 2 simple linear factors, and we cannot go any further than that. So whatever is the number of factors in the denominator, after factorization, whatever is the total number of linear factors, you can count repeated, non-repeated, everything put together. Once the denominator has become all linear factors, post factorization, you just count the number of linear factors, and whatever is the linear factors, you take that many constants. Since in both the cases the denominator has got 2 factors, we will take 2 constants. Okay, and what will happen is you will assume that both the constants could be true, but in the first case we have only 1 constant. So when we solve for the problem, we will assume that it has got 2 constants, and when we solve for the problem, one of the constant will automatically become 0, and that's the trick, and that's what is happening here also. In this case also, when we solve, and if you check out the solution for this, although the output shows only 2 constants, when we solve, we would have assumed 3 constants, and one of the constant would have already become 0. And you can check out the episode, in that I've also highlighted that. And that's the trick that we need to do here. So what will happen, this example 1, which we know that it has got only 1 term and 1 constant, but we will not substitute it this way. Instead of this is what we will do. If you see what I've done here, if this was the given expression, okay, we are initially assuming this 1 constant, but this is not what we will do. Instead of taking 1 term and 1 constant, this whole thing is a term, and taking 1 constant, we'll take 2 constants as below. If you see here, we'll take this and we will just put 2 constants. And how do we put the 2 constants? 1 constant, 1 term will have the same x plus 1 the whole square, the exact denominator, because the denominator will not change. And the other term is this term, which is just a linear factor, okay, with degree 1 overall. This is just linear, but it's a part of the repeated term, but we are not going to put the degree. And when we solve this, when we assume this and solve this, eventually this term will become 0, and all you would have left will be with 1 term. Okay, so that way you don't have to worry upfront whether it has to be 2 terms or 3 terms. You just take as many terms or as many constants that the linear factors are there in the denominator post factorization, and then you solve for the problem. Okay, so what did we see? That now both the examples have the same denominator, x plus 1 the whole square, and the same number of terms and constant in the numerator. That's how we start the problem. A plus b in this case, and in this case also a plus b, and eventually one constant will go away. We will not worry about that. Okay, and the trick here is, if you see, the individual terms in the denominator will have different degrees. Like for example, if you see here, so we had x plus 1 the whole square, right? So the terms that we will take is, we will take all the degrees. We will take x plus 1 the whole square, and then we'll come backwards, and this x plus 1 raised to the 1. So we'll just take the different degrees either in the ascending order or the descending order, and including the linear term. So the linear term has to be there. This is the tricky part, that we have to add and assume 1 new constant term with a linear factor, and the factor is nothing but a part of the repeated the part of the factor which is repeated, but on the linear side. So that's kind of the trick we need to do here, and that's all I wanted to explain. What is that particular specific case where we have some rational expressions for the type 2 repeating linear factors, where we decompose them into 2 constant, 3 constant, and why do we need to take that extra constant? So that's how it works. Okay, so always assume that extra constant is going to be there and start from there, and then work backwards on that one. Hopefully this was a better explanation in accompanying the previous problem that I solved, and hopefully if you just see this back and forth, it will give you a bigger picture of how things work. Thank you.